Okay, so first thing we want to do is this is 8.2 in the old book. I'm not exactly sure what the actual section is in the new book. It might be 7.2. Not a big deal. We'll take care of that later if we need to. Um, One of the first things we want to talk about, however, is the homework. This is not your homework. Whoops, let's not do that. There we go. That is not your homework. Your homework, yuck. Let's try that again. Your homework is out of an updated version of our book. It's going to be on page, let's see, 476 and 477. Numbers 1, 3, 7, 9. That is a 9. There we go. 21, 38, and 53. There we go. Okay. All right. So what we've got is some trigonometric integral techniques that you probably did not go very much into depth during ABBC or AB or BC, depending on how you took the class. Um, so what we're going to do is we're going to go through some of those techniques. If you have already gone through this, this won't seem very difficult for you. First example, we want to be able to take the integral of cosine cubed x. Now, this is going to be under the assumption that you understand the six basic integrals of the six basic the six basic antiderivatives of the sine, cosine, tangent, cosecant, secant, and cotangent. Um, all right, in this example, cosine cubed. You might think trying to do standard u substitution. The problem is if you let u be cosine, which is really the only option, then you would actually need to have an extra factor of sine of x. So off to the side here, let's do green. Off to the side here, if we let u equal cosine, oops, keep hitting this little button here, cosine of x, then du would be negative sine x dx. And the problem is I would need another negative sine of x dx or sine of x dx over here someplace to get rid of it, and I don't have one of those. All I would have is a u cubed, and then when I put dx in there, it would have a sine x in it. So that is not going to do us any good. Let's go ahead and get rid of this. Okay. So what we're going to have to do is we're going to have to use this identity that cosine squared plus sine squared of the same angle equals 1. What we need to do is we actually need to separate, separate the cosine cubed to be cosine x cosine squared x. Then we can use the identity for cosine, or this identity up here, solving for cosine squared. You would subtract this sine squared x from both sides, and you would get the cosine squared is equivalent to 1 minus sine squared. So that's what we'll go ahead and write. So we're going to have cosine x, rewriting this cosine squared as 1 minus sine squared x. There we go. All right, now that we have that, the new integral looks like integral of cosine x 1 minus sine squared x dx. Now we can use a standard u substitution to solve this integral. So if we let u be sine of x, Then what we've got for du is cosine x dx. Now this is a step that if you've had me before, this is a step that I do. You don't necessarily have to do this if you know the more intuitive method. I always solve for dx because that's literally what I'm replacing right here. So dx is going to be du over cosine x. And then from there, I'm ready to go ahead and replace my integral. So let's go ahead and do, I guess, blue. So we'll have the integral of cosine x, 1 minus, now since I let sine be ru, that'll be u squared. My new dx is what I get when I replace this, so that's going to be du over cosine of x. And what you should see is that cosine x divides that cosine x out. And that leaves us with the new integral of just 1 minus u squared du. This should be a relatively easy antiderivative in this case, so we should get u minus 1/3 u cubed plus c. And then we have to remember to go ahead and place the original u back, which was sine of x. So the integral of cosine cubed x is sine x minus 1/3 sine cubed x plus c. And there we have the first one. So you have to use a little bit of ingenuity here to do trig functions, which are not necessarily just cosine of x or sine of x or something easy to do where we know it. We might have to separate them or use some trig identities to be able to solve some of these. I think that was the, oh, nope, there's another one on the page. Here we go. Okay, similar type of example, but now we've got two trig functions. All right, so we've got the integral of sine to the fifth x cosine squared x dx. You're still going to need a single factor of sine here. So what we can do is we can rewrite the integral. Let's see if I can get this to work right. Here we go. We can rewrite the integral as, try that again, sine to the fourth x cosine squared x sine x dx. And really all I did there was I separated one of those signs off of the sine to the fifth to make it sine to the fourth times sine, which is still sine to the fifth. I did that because what I'm going to need is I'm going to need this extra sign out here. And using the identity, we can change this sine to the fourth to be sine squared squared, which I'm not going to write here. But if we think of this as sine squared squared, which is the same as sine to the fourth, we can change that sine squared using the identity that sine squared is 1 minus cosine squared. So that would be 1 minus cosine squared x squared. And then the rest of it still comes down, which is cosine squared x sine x dx. So hopefully you guys can see that 1 minus cosine squared is sine squared, and sine to the fourth is sine squared, which is this, squared. So that's all I did. I took this and made it 1 minus cosine squared squared. Then the cosine squared here and the sine x stay. And I believe that we're probably not going to have enough room on this page, so we're going to have to go to the next page here. I technically would have enough room because I can extend the page. You guys really technically cannot. So we are going to let u, in this case, be cosine of x, which then makes du negative sine x dx. So dx equals du over negative sine x. So we can go ahead and write our integral. Let's use green this time. So our new integral using our substitution, becomes, and this is from the previous page, 1 minus u squared now, that's a u, squared, times u squared, times, and this is where we needed the extra piece, we need the extra sine of x. And then the dx becomes du over negative sine of x. And then once again, you can see that these sine of x's go away. The negative has to stay, so don't lose that. Negative goes out front. And you're going to have to FOIL this and distribute the u squared to get everything into terms that we're going to be able to take antiderivatives easily. So FOILing this is going to give us 1 minus 2u squared plus u to the fourth times that u squared from here times du. Distributing the u squared, now I get u squared minus 2u to the fourth plus u to the sixth du. And then now I can go ahead and take the antiderivative. I could distribute the negative through. It doesn't matter when you do that, just don't forget it. So this is going to be 1/3 u cubed minus 2/5 u to the fifth plus 1/7 u to the seventh plus c. And once again, don't forget to distribute the negative sign, and don't forget to plug back in the original u, which is cosine. So it looks like our final result here is negative 1/3 cosine cubed x minus 2/5 cosine to the fifth x plus 1/7 cosine to the seventh x plus c. And there you have it. All right, one of the reasons why we're doing these problems that we're doing is because in Calc 3 there are a lot of integrals that we have to do where you have to use trig identities. Trig plays a really large part in Calc 3 because we're talking about 3 dimensions and a lot of things. So it's good to go through all these, good to go through all the algebra that's going to be required in doing these as well. So what you should have seen so far is that both of those worked well um, when we had odd powers of sine. So with odd powers of sine or cosine. The problem is if we have even powers of cosine, we have to use half angle identities. So I've given you two of the most common. In Calc 3, you will get to know these extremely well. This is very, very commonly used. So if you don't remember them right now, believe me, after a very short amount of time, you will. All right, so we want to evaluate, and this is now a definite integral because we have bounds. We want to evaluate sine squared of x. So what we have to do is we have to use our half angle identity right here. So we're going to replace sine squared with 1/2, 1 minus cosine 2x dx. Again, very, very common identity. You're going to get to know it very well, and hopefully what you can see is that the only difference between sine squared x and cosine squared x is this plus and the minus. Otherwise, these are exactly the same thing. Makes it a little easier. You just have to remember that one's plus, one's minus, and you have to remember which one. All right, first thing we can do, we have a constant. We can pull that out to the front of the integral. There we go. Now, we can actually integrate this. Technically, you would have to use a u substitution here. We're going to go with a little bit of a shortcut, and if you haven't already learned this shortcut, hopefully you're going to be able to figure this one out pretty quickly. I'll explain it in just a second here. So the antiderivative of 1, of course, is x. The antiderivative of cosine of 2x, what you have here is a linear angle, because 2x is a linear function itself. Anytime you have a linear angle, the antiderivative is going to be the standard antiderivative of cosine, or negative cosine in this case, which is going to be minus sine. The angle stays the same. The only difference is what I put out front, because if you did a u substitution, you would actually get a 1/2. So again, if you have a linear, which we do, angle, what you're going to do is you're going to put the reciprocal of the slope of the linear function, which in this case is 2, out front. So the reciprocal is 1/2. And then we're going to evaluate from 0 to pi. We'll use this a lot. So again, if you haven't been taught this or aren't used to this, we will use that shortcut quite frequently. This works not only for trig functions, but also for doing integrals where we have to use natural logs, and a couple other things. I think maybe some exponentials have that as well. Again, but the angle itself, or whatever we would normally do a u substitution on, has to be linear for this trick to work. All right, let's go ahead and finish this one off. So all we have to do now is evaluate. So 1/2, that can stay there. Now plugging in pi, we're going to get pi minus 1/2 of sine of 2 pi. Sine of 2 pi is 0, so that's 0. Minus, plugging in 0, we get 0 minus 1/2 sine of 0. Again, sine of 0 is 0. And yes, you will definitely need to know all your trig values quite well. So that's 0, that's just pi, so we get 1/2 of pi. It looks like the integral here is pi halves. Done. Moving on. All right, same general idea. This one's just going to take a little bit longer, it looks like, because this is sine to the 4th. So we're going to have to break this one down. This is what is called power reduction, by the way. This is something, again, we're going to use heavily in Calc 3. So the first thing we want to do is we want to rewrite this as the integral of sine squared x squared dx. Because now what I can do is I can go back, that doesn't look very good, I can go back to my half angle identity for sine squared and rewrite the inside of that parentheses as 1/2 1 minus 2, oh, that's not right, try that again, 1 minus cosine 2x. Now this whole thing is what's inside this parenthesis, so that whole thing gets squared. Alright, so I have to square the whole thing here. So I got to square the 1/2, which is 1/4. I have to square this, which is a FOIL. 1 minus 2 of these, which is cosine 2x. And then squaring that is going to be plus cosine squared 2x dx. Alright, first thing I see is I can pull that 1/4 to the front. Makes things a little bit easier. There's going to be an additional problem that I see here, though. This, the one, I can take an antiderivative. That'll be easy. This one, because it's not squared, it's just going to be that little trick that I showed you before. We can actually do that one pretty easily. Multiple angles are easy to deal with as long as it's linear, as long as this whole thing here isn't squared or raised to another power. This one's going to create another problem. It is now a cosine squared, which means I am now going to have to, oops, why did that turn to black? That's weird. Very strange. I am now going to have to do another reduction on this one. And this is an important one for us to see. There's something else that's going to happen here. So cosine squared was 1/2 1 plus cosine. Now, you might be tempted to write a 2x here. The problem is the 2x is not 2x. Really, it means double the angle that we had before. Well, the angle here is 2x. So if I now double this in the place of the 2x, it's now going to become 4x. And another big parentheses, and then dx. Let's move this down a little bit. So as you can see, this is becoming a little more lengthy. There is a bunch of algebra in these, so just be patient, take your time. You guys would not be in this class if you couldn't do some algebra. 1 minus 2 cosine 2x. Distribute the 1/2 through here, plus 1/2 plus 1/2 cosine 4x dx. All right. We don't have to. I'm going to just, to make it a little bit easier, combine these constants. 1 plus 1/2 here is 3/2 minus 2 cosine 2x plus 1/2 cosine 4x dx. And now we can take antiderivatives. 3/2 x. Remember that you've got a 2x here, so this is going to be minus. This will become a sine of 2x. The reciprocal of the slope here is 1/2, so 1/2 times 2 is 1, so I'm not going to write that. Antiderivative of cosine is going to be negative sine, so it'll be negative sine 4x. Reciprocal of 4 is going to go out front, which is 1/4, so 1/4 times 1/2 is 1/8, plus c. So the last thing I'm going to do is distribute the 1/4, and we will be done. So that's going to give us, it looks like, 3/8 x minus 1/4 sine 2x minus 1/32 sine of 4x plus c. And I believe that that is the answer to that problem. Yep, we're good. All right, I think we're going to come back in a second video. Yeah, we're going to start with things other than sine and cosine now. So we're going to come back in a second video and do some of the other trig functions. We should be able to get this done in 2 videos.